skip this because it's not supposed to be in here. The other important parametric analysis I'm going to talk about is the MPSH basic water rate. Notice that on this graph, the green line actually represents MPSH available, and the blue and the red line here represents the MPSH required in different pump speeds. The whole idea of this graph here is to identify the critical points in order to prevent cavitation from happening. And just quickly introduce what cavitation is for those people who don't know. Cavitation is basically when the water pressure in the casing falls below the vapor pressures, and the bubbles will start to form, and this will cause wear to the pump and ultimately then damage to the pump. Yeah. Okay. MPSH available can be actually calculated using that equation over there. The P stands for the pressure in the feed vessel. H stands for the liquid height above the suction cap, and PF is the pressure loss in the pipeline, and the PV is actually the vapor pressure. MPSHR actually can be correlated using the following graph. If by giving the water rate as well as the pump speed, we can actually calculate the MPSHR. So the two critical points identified in this case are the intersections between the two different types of curves. We can see that the ending points on the right-hand side of these two critical points means that the cavitation will occur. If we draw a line to the intersect with the x-axis, we can actually see that approximately 2,000 barrels and also 2,700 barrels. And if you remember earlier on, I mentioned that the water rate actually ranges from 50 barrels to 2,000 barrels. So actually, this illustrates that the pump design here is adequate to prevent cavitation from happening. Finally, let's jump into the conclusion. The first important conclusion is that we identified the design constraints and also established the design basis. The second conclusion is that we selected the horizontal separators due to many reasons, and also we selected the screw-type air compressors. We also decided to choose a centrifugal pump here. We performed the mass balance and energy balance on all three scenarios, followed by produce of the PSD layout as well as initial specification. We also experienced the high compressor discharge pressure and temperature during the initial design stage. Finally, the pump analysis shows that the pump design is adequate for pumping and cavitation prevention. Jumping to the recommendations here. First thing is that in the future, side access to the well site should be made available to students for taking measurement purposes. Also, we should have a better document and data management system. And also, projects, because so many things have been changed since we've been doing this initial design stage. Therefore, we need to sit down with the project management as well as the design team to reconfirm our project scope. The next recommendation is very important. I strongly recommend that the future component of this project is undertaken by two students, especially with mechanical engineering background. Also, the professional participation should be encouraged. I was really grateful to have centers to help me this year, but I also encouraged to get all the engineering consulting firms involved, such as GPA Engineering as well as Wally Partners. Also, university involvement should be encouraged because I come from a chemical engineering background. I know that the chemical engineering department actually have a lot of expertise to offer in the areas of process and the facility design. So if we can get a chemical engineer supervisor next year, it would be extremely beneficial to the department, to the students as well as to the project. Just quickly talk about what we will be doing next. Strongly recommend additional parametric analysis on the back pressure as well as the flow regime. Especially the flow regimes, very, very important. Also recommend the multi-stage compression study, safety and analysis and plant operability study. This includes PIDs as well as Hauser-Hausen, sustainability and environmental assessment, detailed design phase, as well as, if we have time, making inquiry on the specifications as well as obtaining bid quotations. I would like to thank the following people, especially my supervisor Mattia and Thomas Moore, for their encouragement and guidance in the past 8 months. Also would like to thank the downhole completion team, Simon and Adam, for their cooperation during the project phase. These are references.
Thank you, Han. So presentation is open for questions. Please go ahead.
Okay.
Why did you choose the horizontal separator?
Okay, I choose the horizontal separator. Okay. Because I don't really have enough time, that's why I didn't really explain it. The reason why I choose the horizontal separator, first of all, because it is cheaper and smaller for given gas capacities compared to a vertical separator. And second of all, horizontal separator actually has better separation, and because the flow entering the separator is actually the settling direction is actually perpendicular to the flow direction. This actually allows the liquid to be, better settled out, and also the horizontal separator provides a much larger liquid interface, which again helps with the separation. The other thing, the other reason why I decided to use the horizontal separator was because when we did some initial calcs, we found that the dimension of the vertical separator is 2.4 meters. There is a clearance height from the ground floor to the first floor is only 2.8 meters. On top of the separator, you have to consider the pipelines and all that kind of stuff. You won't be able to install a vertical separator. That's why I choose horizontal separator. If you want to know about why I choose the screw type air compressors, the primary reason.
Go ahead.
Because a screw type compressor allows for a high compression ratio. This is due to the reason that because there is coolant, lubricant or coolant, was introduced to the screw type compressors. It actually allows you to cool down your temperatures, which subsequently allows you to have a larger compression ratio. And also, screw type compressors, it has less moving parts, so less maintenance is required. And the reason why I choose centrifugal compressors because of the abundancy and as well as availability. Also, centrifugal compressor can handle whole lot of different kinds of flows, such as by including little small particles or even small solids, And also, centrifugal pump requires less suction head, which is ideal for this case. Yes, these are the main reasons.
I noticed one of the risks in your design seems to be the availability of power.
Yes.
It says 50
55
kilowatts.
kilowatts. Yeah.
Your design has close to 45 kilowatts of power usage, which is, it doesn't leave you a lot of room there. How would you, going forward, if the project was to continue forward, how would you manage that risk? Have you really got 55 kilowatts available?
We actually have 55 kilowatts just for the building, but then I spoke to the university management team. They were actually saying if the project do go ahead to the next phase, they're actually talking about bringing on more power to this building, which means more facilities will be built in order to accommodate the additional power requirements. So, yeah.
There is an option to increase the power.
Yes. I actually assumed allocated 50 kilowatts to either pumps or compressors. I leave 5 kilowatts just for contingency. Yeah.
Given that you're pumping water and air mixture in some parts, do you think corrosion could be an issue?
I'm actually mainly pumping. Are you talking about the pumps?
No, in the flow lines separated. In the lines and the separator, you've got two-phase flow.
Yeah. For the purpose of this exercise, I did not actually take that into consideration. I just briefly touched on pipeline design because I'm running out of time. I guess that could actually go into future recommendations for the next stage. Yeah. Okay. Any more questions from people?
Thank you.
From Ellen, question?